Hi there, Miss Barber here. This lesson is titled Average Rates of Change. In this lesson, we bring together from algebra the definition of slope and limit concepts of calculus to approach the concept of instantaneous rate of change. We make this transition starting with the basic definition of the slope and then interpreting that definition as the average rate of change. Let's begin this lesson by looking at the graph provided. The graph is provided in an xy plane. It is a smooth polynomial whose drawing begins in the second quadrant, and it has a smooth decrease which intersects the negative x-axis, makes a smooth turn, increases again, intersects the negative x-axis again. While it increases, it intersects the positive y-axis, increases in the first quadrant, and turns around to decrease. It continues to decrease while intersecting the positive x-axis. Along the x-axis, positive, the points A and h units to the right, a plus h is marked, and along the positive y-axis, the corresponding points f of a plus h is marked, and above that, the point f of a. Now, we are also given a decreasing line connecting 2 points through the corresponding x value of a and a plus h. Let's recall how to compute the slope. The slope is denoted as rise over run, but it's actually change in rise. The triangle means delta, it's little change, over little x. So delta y over delta x. We are looking for the change, so we would do y2 minus y1 divided by, for delta x, x2 minus x1. Let's change those points in the formula to correspond with our drawing. So I could say that x1 corresponds to a and x2 corresponds to the a plus h. Let's replace. So y2 is actually f evaluated at a plus h minus y1 is the function evaluated at a. Now let's continue some more. For the denominator, x2, we replace with a plus h, and then we subtract x1, which is a. We can simplify it a little bit further, and we would have f of a plus h minus f of a divided by h. And of course here h cannot be 0. Okay? And so that is called a difference quotient. It is used to find the slope that we call the average rate of change. We have another definition. So for y equals f of x, the average rate of change, also called the slope of the secant line from x equals a to x equals b, and for our drawing, b corresponds to the point a plus h. Okay? That average rate of change is f of b minus f of a divided by the quantity b minus a. Example, find the average rate of change of f of x equals 5x squared minus 3, starting at a equals 1 with a horizontal distance of h equals 3. Let's get used to the formulas. The average rate of change formula, one of them was f of a plus h minus f of a divided by h. Now let's match the parts. We are given in the statement of the problem that a equals 1 and h equals 3. So let's make that substitution. This would be f of a is 1 plus h is 3 minus f of a, which is 1, all divided by h, which was 3. This can be further simplified so that we get f of 4 minus f of 1 divided by 3. Let's compute each of those parts. F of 4 is equal to 5 times 4 squared minus 3, and so that's equal to 77. Let's continue. So f of 1 is equal to 5 times 1 squared minus 3. 5 minus 3 is 2. Let's put those values into our function notation. So we replace f of 4 with 77, f of 1 with 2, and we divide that by 3. Let's continue with more arithmetic. So you get 75 divided by 3. We can conclude that the average rate of change is 75 divided by 3, which is 25. Example, the revenue in dollars from the sale of X planter boxes is given by R of X equals 20X minus 0.02X squared. What is the average rate of change in revenue if production is changed from 100 to 250 planters? We are asked for the average rate of change. That informs us that we need to use an average rate of change formula. Average rate of change. This time we are given a starting point and an ending point, not the distance between them. So what we're going to solve is we're going to need the R of B minus R of A divided by B minus A. Let's go ahead and identify the parts. So we'll say A is the starting point, which is 100, and B is the ending point. We will have increased to 250. So filling in those numbers, we would get R at 250, so the revenue at 250 minus the revenue at 100 divided by B, which is 250, minus 100. Let's solve the separate function values. So the revenue at 250 would be 20 times 250 minus 0.02 times 250 squared, and in your calculator that will come out to 3,750. And the revenue when you sell 100 of these boxes will be, let's see, 20 times 100 minus 0.02 times 100 squared. Compute this in your calculator, and the output is 1,800. Let's put those values together in the formula. We will replace the notation R of 250 with its computed value of 3,750, and replace the value for R of 100 with 1,800. And let's do the subtraction. 250 minus 100 is 150. When you use your calculator, make sure that you solve the 3,750 minus 1,800 in parentheses, and when you finish, the number is 13. Now, I'd like for you to be able to explain what that 13 is. We are asked for the rate of change of the revenue, and what we find out is as you increase production from 100 to 250 planters, we have an average increase over those 150 new planters of $13. Now that we have looked at two different forms of the formula for the average rate of change, let's look at the graph, the secant line. The secant line is determined by a line that intersects two different points on the graph of a function. The tangent line, by definition, is a line that touches just one point of that graph of the function. When computing the rate of change of a function at a point, say a f of a, the tangent line provides an instantaneous rate of change. The secant line provides just an average rate of change. While we define a tangent line as the line that touches the graph at just one point, let's keep in mind that that tangent line could conceivably across multiple points on the graph, we are just concerned with the one point of tangency. For the provided graph, find the slope of the tangent line through the point x equals -1. The graph provided is a downward-facing parabola. Its vertex is on the y-axis at 4, and it is symmetric about the y-axis with x-intercepts at -2 and 2. The tangent line is dashed. It is increasing and drawn at the point -1, 3. Now for the graph, we also see that the tangent line touches the graph of the function. So let's go ahead and mark that as -1, 3. We must look carefully at this, and we see that the tangent line also touches another clearly indicated point in the xy plane, and that appears to be at 0, 5. Now, we're going to use 2 points to get the slope of the line, but it will be the slope of the tangent line because that line touches the graph at only 1 point. Let's recall. We compute the slope as delta y over delta x. That's a little change in y over a little change in x. So let's make it fit the formula for the slope, which is y2 minus y1. Divided by x2 minus x1. So we'll have 5 minus 3 divided by 0 minus -1. So that'll be 2 over 1, or we get that the slope of the tangent line is 2. Example, for the graph provided, draw tangent lines through the points where x equals a, x equals b, and at x equals c. Determine whether the slope of each line is positive, negative, 0, or undefined. The graph presented is a polynomial function located in all 4 quadrants. It decreases starting in the second quadrant, intersects the negative axis on its descent, makes a smooth turn, and increases until it hits a high point on the negative y-axis. It continues to decrease and then makes a smooth turn, begins to increase it, and while increasing, it intersects the positive y-axis and continues to increase. This graph is symmetric about the y-axis. So let's look at the point x equals a. It is marked on the graph with a dot, and we draw a tangent line at just that point. And we see that at x equals a, the graph of the tangent line is moving downwards, so it is negative. Now let's look at x equals b. To the graph, there's a point marked on there for us. Draw a line that tangents or butts up to that point. And so the tangent line is increasing. So we will say that at x equals b, the tangent line is positive. And now let's look at the point x equals c. The c point marked on the graph is at a low point in the 4th quadrant. Drawing a tangent line, it appears to be horizontal, and a horizontal line has a slope of 0. So let's summarize. At A, the slope is negative. At B, the slope is positive, and at C, the slope equals 0. Example, for the provided graph, determine where the tangent line is horizontal or vertical. We have a graph that begins its drawing in the 3rd quadrant. It increases up until the negative x-axis at the point -2, increases vertically up, and then starts to increase again, moving horizontally. In its gradual increase, the graph intersects the positive y-axis between 2 and 3, increases until about x equals 2, and then begins a gradual decrease downwards. We need to find where So we're looking for x values where the tangent line is horizontal or vertical. Let's begin with vertical tangent line. Occurs at x equals some value. Looking at this graph, we see that the graph of the function vertically intersects the negative x-axis at x equals -2. Now we need to find where a horizontal tangent line occurs. So we'll say tangent line at, and we need to determine, just following along the shape of the graph, it appears that we get a tangent line that is horizontal to the graph when x equals 2. Example, for the provided graph, determine the intervals on which the slopes of the tangent lines are positive and the intervals where they are negative. Let's recall that in order for any line to have a positive slope, the graph of that line must be increasing, and for any line to have a negative slope, the graph of that line must be decreasing. We can get where the slopes of the tangent lines are positive by observing where the graph is increasing. Let's observe, reading the graph from the left to right, at approximately -1.6, all the way to the origin, the graph is increasing. So we'll say tangent line slope is positive where the graph is increasing. The first interval in which that occurs is -1.6 to 0. And then it increases again from x equals 0 to what appears to be +1.6. So we'll say union from 0 to +1.6, and that appears to be the only two intervals on which the graph is increasing. Now we'll conclude that the tangent line slope is negative where the graph of the function is decreasing. Let's again observe the graph from the left to the right. The first decreasing occurs where the drawing begins in the second quadrant, and the function decreases all the way until the x value of -1.6. So the first interval would be -infinity to -1.6. Then we have increasing and increasing again. We have another decreasing interval, and it begins at an approximate x value of 1.6 and continues to decrease until the x value of 3. And then, it continues to decrease beginning at 3 and going to +infinity. Often a good question is asked, first considering the increasing, is why do we not just say that the graph is increasing from -1.6 to +1.6? And that is because we have a resting point at the origin. So this graph has horizontal tangent line at x equals 0. Let's see, are there any other points? Yes, the next tangent line that we have at x equals 3, and there's one more. The remaining horizontal line kind of got lost in my sketchings, but it occurs where the function changes from decreasing and then increasing, and that happens at x equals -1.6. So this occurs again at x equals negative 1.6. Exercise. Find the average rate of change of the function f of x equals 3x squared minus 5x from x equals 1 to part A, x equals 3. So to find the average rate of change, we will use the formula of f of b minus f of a divided by the quantity b minus a. Now let's substitute in the values. So for b we'll put in 3. F of 3 minus for a we'll put in 1. F of 1 divided by 3 minus 1. Now let's find the specific function values. For f of 3, we'll have 3 times, and for the place of x, 3 squared minus 5 times, and for the place of x, 3. When this is computed, we will get 3 times 3 times 3, which is 27 minus 15, and that's equal to 12. Let's find the function value at x equals 1. That'll be 3 times, and for the x, put in 1, so 1 squared minus 5 times 1. This simplifies to 3 minus 5, which is negative 2. Now let's put this all together. So for the average rate of change, for f of 3, we'll replace that with 12 minus, for f of 1, we will replace that with negative 2 divided by 3 minus 1. Let's continue with the arithmetic. 12 minus negative 2 is 14. 3 minus 1 is 2. And so the average rate of change is 7. Part B. Find the average rate of change of f of x equals 3x squared minus 5x from x equals 1 to x equals 1 plus h. So let's use the average rate of change formula, which is of the form f of 1 plus h minus f of 1 divided by, we would have 1 plus h minus 1. This simplifies a little bit, so we'll get f of 1 plus h minus f of 1 all divided by h. Now let's find each of the components. I'll begin with f of 1 plus h. So we're going to replace x every place we have it in the function with 1 plus h. We will get 3 times 1 plus h squared minus 5 times 1 plus h. Let's continue. The 1 plus h squared means 1 plus h times 1 plus h. For good measure, let's just go ahead and write that. And we'll continue to simplify. So we'll have 3 times multiplying the two binomials. 1 times 1 is 1, plus the sum of the products of the inside and outside terms, which will give us 2h, and then plus h times h, which is h squared. Now let's continue by distributing the 5, so you get minus 5 minus 5h. I'll bring that down to the next line, minus 5 minus 5h. And one more, we'll distribute the 3. 3 plus 6h plus 3h squared minus 5 minus 5h. And some of these terms combine very nicely. So for example, 3 minus 5 would give us negative 2. 6h minus 5h gives us just 1h. And there's no other square term, so we'll have 3h squared. Okay. And we computed f of 1 previously in part A, which I believe was f of 1 equals negative 2. Now, let's combine it in the formula. So the average rate of change, replacing the f of the quantity 1 plus h with the output of negative 2 plus h plus 3h squared minus f of 1, which would be minus f of 1 is negative 2, divided by h. Let's continue to simplify. Observe that we have a negative 2 minus a negative 2, so those two constants cancel each other out, and in the numerator we have h plus 3h squared divided by h. We have a common factor in the numerator. Factor out the h. So h times the quantity 1 plus 3h divided by h. Those h's cancel, and we finally get the simplified version, which is the average rate of change from x equals 1 to x equals 1 plus h is 1 plus 3h. Find the average rate of change of f of x equals 3x squared minus 5x from x equals 1 to x equals 6. We are given a hint to use the solution for x equals 1 plus h, which we solved in the previous problem. Let's recall, when we have the difference quotient formula, which is for the average rate of change, we write as f of a plus h minus f of a divided by h. What we know is that h is the distance, between the initial point a and a plus h. So if we are going from 1 and the final point we're going to is 6, we know that h equals 5. 1 plus 5 gives you 6. Now let's use the solution from the previous problem. We found out that the average rate of change when computed was equal to the equation 1 plus 3h. We know what h is, so now we can find the average rate of change from x equals 1 to x equals 5 by replacing the h with just 5. And so 1 plus 15 will give us 16. Just for a little assurance, let's check with what we did in Part A. In Part A, we did from x equals 1 to x equals 3. So the distance between 1 and 3 gives us an h of 2. Let's use that simplified form. Average rate of change is 1 plus 3h. This would be 1 plus 3 times 2, which is equal to 7, the same value we previously got for Part A.